should turn the orange thing. Orange. Turn it to that, and then you will just shoot up. Oh, yeah. But that thing shouldn't be shooting up.
Okay, we'll get started very shortly. So the title of the talk is slightly changed, but actually it's still about multi-armed bandit as well. So this is more general.
Yes. So, oh yeah. Okay. So this is just this is it's our multi-armed bandit.
Okay, maybe we should get started, just to keep to the time. So we are very fortunate to have Professor Irwin giving his second talk. This is not nearly as theoretical as the first one. Actually very informative, very interesting. So I'll let him take over.
Sure.
He's a more dynamic speaker than I am, so Irwin, please.
Should I use this one?
Yeah, okay. Thank you. Well, welcome back. I know that is slightly different from the topic that is in your program, but it is really, I'll guarantee you this is the same topic that I'm going to talk about. This morning I talked about randomized algorithm, and right now I'm going to talk about online learning. And this is not about MOOC, it's not about that type of online learning. But it's an online learning that we encounter when we encounter streaming data. So that when the data is coming in at you very fast, for example, and you got to make a decision at then what you need to do next. And that's what I mean by online learning. Okay? So before I go on, let me share with you the problem we're trying to solve. Very similar to my talk in the morning. I'm going to begin with a comment, and this is the comment. And it's a secretary, And this secretary is very adaptive because you can see that in tray and out tray are very piled high with documents. And she's actually be able to buy a chair that can move up and down and to finish her work. And in fact, this is a good secretary that you would like to hire, right? So this is good. We look for people who can quickly adapt to changes in the workplace. And I hope that we all could somewhat adapt or learn from our environment in a new workplace. Here's the problem. You have not heard of a secretary problem. This is the problem. And I want you to think about a potential solution. Okay? So, you have secretaries that you want to hire. That's the problem. Okay? You're the boss, and the secretary are lining up to come for the interview. Okay? And the question to you is this: how do you find the best secretary? If there are a number of people here, so let me describe the scenario to you. The scenario to you is this. You can only interview candidate one at a time. Okay? So there are maybe 100 people lining up outside. you could only interview candidate one at a time. You could only make a decision to hire that candidate or not hire the candidate, okay, after you've done the interview. So if you hire the candidate, then you stop all other interviews, okay? If you say, I don't want to hire this person, then you continue to the next interview, okay? Okay. This is a clincher too. You cannot go back and hire another candidate. So obviously this is not real life, right? Real life, you continue to interview 10 or 100 secretaries, and you can choose the best one, okay? But in this case, you cannot go back. So you interview 10, and you decide to hire 11th one or the 12th one, that's up to you, right? But you cannot go back to hire, say, the first one or the second one. And lastly, you know the total number of candidates to be interviewed. So you know like 100 people there will be interviewed, okay? It's not infinite number of candidates, okay? So this is the assumption. Okay, here's the problem. This problem is very similar to what a marriage problem, Sultan's dowry problem, and the optimal stopping problem. This is what we call a class of sequential decision problems. Why is it called sequential? Because things coming in a sequence. You, the person, has to make a decision to stop or to go on. Okay? So this is what we call a sequential decision problems. Let's take a look at this. So the naive solution is that you being a computer scientist, you will say, hey, I could simulate this scenario. So what I do is this, my strategy is this. Obviously, one strategy is to hire the first person. Okay, assuming that there are 100 people, and each one has a ranking between 1 and 100. So you have basically a permutation, okay, of a true ranking of 1 to 100. But you permute it, so you randomize this 100 people, okay? And my naive strategy is to hire the first person who comes up. I don't care. I just hire the first one. Then let me ask you this. What is expected probability of that person is the best person? What would that be? 1 out of 100, right? 1 out of 100 because it's randomized permutation. So if I just pick the first one, I only have 1 out of 100 chance that this could be the best candidate, correct? Okay? Similarly, if I interview 99 of them and then pick the last one, okay? If I interview 99 of them and pick the last one, what is the probability for me to get the best candidate? And that probability is also 1 over 100, correct? Okay? So, the strategy is this. What if I interview 1 people in one simulation, I interview 2 people in another simulation, I interview 3 people, 4 people, 5 people, 6 people, I interview 50 people, okay, and I know the best of the 50. Then the 51st, if that 51st person is better than what I have seen in the previous 50, then I'll hire that person. So let me rephrase that again. I can interview 50 people first and not choose anybody. So I explore the situation. I know out of the 50, there is a best among the 50, but that may not be the best of the 100, okay? If I know the best of the 50, on the 51st I come out, my strategy is to say, if that person is better than the one that I've seen in the first 50, then I'll hire the person. Then my question is, what is the probability of you obtaining the best person? Is that clear? Is that clear? Is that clear? Let me see, is there a way that I can present it? Basically, what this exploration is to say that I will evaluate some set of candidates, secretaries. I learn what is the best among these candidates, and then whoever I do this, the next one, whoever is better than that candidate, I'll just hire them, okay? And will I actually find out the best among the 100? That's what I want to do. Now, you can set this up very easily on a computer program because you could permute 1 to 100, okay? So when you just look for it, if you want to search for 10, like between candidate 1 to 10, maybe 33 is your highest ranking, right? And then the 11th one, if that 11th one is greater than 33, then you hire that person. Okay, what is the probability of that person being the best person? Well, it turns out that if you simulate this, you permute the sequence, you set the number of candidates to explore, and then set the benchmark and choose the best candidate, and then you run 10,000 times, right? What do you get? Would you actually get something like this? Totally symmetrical? Because if you don't explore, you just hire the first person, and you don't explore, you explore all 99 of them and hire the last person, the probability of you getting the best person is 1 out of 100, because you don't have 100 candidates. So you are 1 out of 100 here, you're 1 out of 100 here. But my question then is this curve symmetrical? And what is the highest probability that you will be getting the best candidate? Okay? That's a question that I would like to ask. It turns out that if you do the simulation right here, this is actually the empirical result. So if you simulate it 10,000 times, okay? This is what you will get. And why do you get this? You will get actually X. This probability, this one, the best one, is that you interview 37 candidates. 37 candidates, and on the 38th one, if the 38th one is better than any of you interview 37, then you pick that one. And the probability of obtaining the best candidate is y is 0.37. You got 37% of the time that you will pick the best candidate after you interview 37 people. Interestingly, it's not 50. If you do a 50, you will see that your probability of getting the best candidate is actually less than 37%. Okay? This is what we call it, a sequential decision problem, because along this line right here, you could interview nobody, you could interview 1 people, 2 people, 3 people, 4 people, 5 people, and so on and so forth, all the way up to 99 people, and you select the last one. Sequentially, when do you stop? And this graph shows you that it is best to stop at x equals 37. Because you will have the highest probability of 30% of getting the optimal result. Okay? This is the solution of the secretary problem. Now, why is this important? Because it turns out that this optimal strategy was actually discovered back in 1989 by Ferguson. And what he discovered is this. Reject the first n divided by e. E is the natural number. So if we put n is equal to 100 and divide it by this, you get a 0.37n. Okay, 0.37n. And then you accept the first one above the top category after this. The highest probability is 1 divided by e, which is 0.37%, 37%. Okay, because 100 here and 1, they're just off by 2 digits. Okay, so that's why it's always this 37 comes in here and comes in here. Okay, the highest. But using a different n, you'll get something different because the highest probability does not change, 37%. But the number of candidates that you're going to pick will be different, right? If I have 50 candidates it will be what? 50 times 37, which is about, I interview what? About 19 people. 19 people. Then I pick the best one after the 19 people. Does that make sense? Okay. So what this is really what we call an optimal stopping point. When do I actually stop in this sequential process? When should I buy a stock? At what time is the most optimal time? Okay? And many decisions, when is the best time to make that decision to do something or not to do something, falls into what we call a sequential decision problem. Okay, so, very interesting. For guys and girls in here, I'm using it from the perspective of guys. You know, this is a marriage problem. The marriage problem says that, should you spend time to develop a relationship with your girlfriend or continue to look for different girlfriends? Right? You have a finite number of resources, so should you actually see many girls, more girls to explore different possibility of girls? Or you should focus on one and just stay with it. So in some ways, this is also a question that you may face. Because I hope that you don't have multiple boyfriends or girlfriends, obviously. You do this sequential processing at a time, right? But you have to make a decision, because when you marry, you select that person who you want to marry, right? Okay. Now, from that earlier problem space, we could generalize this to this multi-armed bandit, okay, problem. So let me transfer that into this context, okay? And how does that translate that into context? Here is a set of machines here, maybe 4 right in front of you. Every time you pull is it requires $1 for you to pull that, okay? You have $1,000. $1,000. So you could pull this at least 1,000 times. Assuming that you win some, you could have more, but at least you could pull this 1,000 times. My question to you is, there are 2 questions I'm going to ask. Oops, sorry. Oops. Okay, let's go back. Let's go back. So, this is basically exploration versus exploitation. I could continue by $1,000. I could do this 1, 2, 3, 4 times, 250 times. I could explore the whole space and come up with a machine that gives me the highest probability. Then I would say, hey, this is a good machine. Or I could explore differently with different weights. And maybe that will actually give me a higher return. That will maximize my profit. Right? So there are 2 ways to actually do this. Explore the space or exploit that machine. Okay? So this is what we say that this kind of multi-armed bandit problem is basically a problem. It's a trade-off between exploration versus exploitation. Okay? Will you explore, will you exploit? So I pull this, it requires $1, I get different rewards. So the 2 questions I'm going to ask. One is, among these 4 arms, if you have 1,000 times to try this, can you tell me, first of all, which arm is the best arm? Which arm is the best arm? And second question that I'm going to ask you is this. If I give you $1,000, what is the maximum reward that I could get by pulling this 4 machines? Whether I pull each one 250 times, or I could pull something because that might appear to be having a higher probability of others getting my reward back. So I pull that more than the others. So there are 2 questions. Which arm is better? The second question is, how much money am I going to get back if I give you $1,000 to do this? So this is a very practical problem. So if you go to Las Vegas or some gambling places, you can actually use this to actually predict and run the strategy and see which one is better. Okay, so let me show you a scenario that I simulated. Here is the round, and here are the arms. Arms 1, 2, 3, 4. Here's the round 1 to 4. So the first 4 times, what I'm going to do is I pull this, I pull this, I pull this, I pull this. Okay? So now is this. I have a very dumb strategy. It's called mean value strategy. So what that strategy will do is this. Once I pull this, if you give me something that is good, I will continue to pull that arm until you give me something bad. It's almost like greedy algorithm. Okay, this greedy algorithm to see whether this works. So if I pull this 4 times, you will see that this will give you 1, this returns something, this returns something, this does not return something. Then what I'll do is I'll go to the others and select randomly 1 out of 3 because they're all 1, 1, 1. So I select randomly, I select this one. Unfortunately, the round 5, when I pull that, this arm 1 give me 0, nothing. Okay, so I just leave that. I'll randomly select this. And I pull this, you will see that, oh, the arm number 2 give me actually a good result. So I will actually pull this, 1.5. Then I pull a 3rd time. Guess what? The 3rd time didn't give me anything. Okay, so 1.5 become 1.3. The 4th time I pull, it still didn't give me anything. So I get 4 divided by 4, which is 1. So between the 2 then, I will randomly select, and this becomes 2, 2, 1.5. I can simulate this and go on and on and on, right? So my mean value algorithm may work in finding a good one. But what's the problem here? What's the problem? The problem that you will never explore this arm. Never. Because this time, the first time it hits 0, and all other are non-zero value. Okay, the worst case is that out of these 4, there's only 1 arm that actually shows up to be positive, to give you reward. Then you will always explore that particular arm. And that's not good, that's not what you want. Okay? So this mean value, although it kind of seems to work in this scenario, it doesn't work in many, many situations. Okay, let me give you another one then. Let's do this, mean value plus standard deviation. Okay? I had to introduce a concept of standard deviation. Statistically, you know what standard deviation is. Okay? And it turned out that in big data too, the more data that you have, the more accurate that you can predict certain things. Right? The more data you have, the more accurate your outcome, your prediction will be. In the similar sense, the more data that you have, the smaller the standard deviation will be. Okay? So standard deviation, the larger deviation, means that your prediction area will be also large. And is not very good. But when you have small standard deviation, then that means that your prediction is actually quite good. Okay? So what we want to do is this. We begin with some kind of standard deviation for each one, in addition to the mean value. So right here, what we simulate is this. On 1, 2, 3, 4, same thing. I pull, but I also have another value, plus 1, plus 1, plus 1 here. That is my standard deviation. Okay? So earlier, same thing. I pull this, 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 this. I also get 1, 1, 1, 0. So I get 2, 2, 2. But look at here. This is a non-zero number now. Non-zero number because it has a standard deviation of 1. Okay? I go through this process as earlier, and you can see that eventually maybe this gets 0.9, this gets 0.9, this gets 0.93, this gets 1, and guess what? The next pull, I'm going to pull this. Okay? And then I could go on, and you can see that this is 1.8 and so on and so forth. Right? Now, it turns out that this value right here, what is that value telling me right now? That value is telling me which one of the arm is the best at that given time. At that given time. Because this is, in some ways, cumulative, normalized over a period of time. Does that make sense? Okay? So if I look at this right here, I would say that ARM 4 is not very good. ARM 1 to 3 are probably better ARM. But if after 12 round right here, I could say that ARM 4 actually is better than other ARMs. Okay? Mean value. Because that tells me the reward that I'm going to get. Okay? Now, there's some things. Actually, standard deviation, you want to be as small as possible. Okay? And this mean value, you want to be as large as possible. But I'm just saying that you can have a measure in such a way that you can tell you which one's best at any given time. Okay? So here, you can see that it will overcome the starvation problem. The starvation problem is that earlier, ARM 4 will not be explored. But now, ARM 4 will be explored. Okay, let me introduce a stochastic thing here now. Oh, before we do that, I need to introduce what we call it upper confidence bound, UCB. Okay, upper confidence bound. Why do we need to use a UCB? It turns out that for many of the optimal strategy situation, okay, the result is we want to actually get to a bound of UCB as close to the UCB as possible. That will tell us how confident we are in getting that upper bound, right? So earlier, I could say that with a confidence value of certain things, this machine is the best, right? Because we don't know the reality, but after many rounds of pulling this strategy and whatever strategy you come up with, what the theorists or computer scientists want to do is to prove that your strategy has a upper confidence bound, okay? So that we could compare different strategies. My strategy, there are two strategies I introduced to you. The first one is called mean value. The second one is mean value plus standard deviation. The two strategies. Which one is better? We could prove the UCB for those two algorithms and know which strategy is better. Okay? Now, so the problem could be expanded a little bit. The solution can be expanded a little bit. Is that we can also have what we call an epsilon greedy strategy. And what is epsilon greedy strategy? Is this. With the mean value, with the standard deviation, let's throw in some randomness, stochastic things. So, basically what we want to do is that with probability of 1 minus epsilon to play the best arms, the set of best arms. And with a probability of epsilon to randomly select the inferior arms. So if we were to go back to this scenario, okay, if we apply the epsilon strategy, there is 1 minus epsilon probability that I will select from these three arms. And there is a very small epsilon probability that I will select this arm. So to prevent what? Starvation. So I will not starve this particular arm. Does that make sense? Does that make sense? Okay, so you might ask, why do I do this? Okay, so with those three solutions I just shared with you, let's take a look at some of the variants, okay, of the multi-armed bandit problem, okay? We call it MAB problem. There are some variants. First, instead of finding one best arm, I may ask you to find the top K arms. Okay? Now you might say, hey, is that the same thing as finding the top, remove that, and then finding the second top and remove that, and finding the third top and remove that? Yes and no. Okay, you could do that, obviously, but there may be some other constraints that we need. Because we might break this down into 1 group, 2 group, 3 group, 4 group, and we might say we want a top from each group. Now obviously you could separate this into that. Or I might say, give me the top 4 from this. Then you may need all 4 from one group, right? And maybe 2 from this group, 2 from this group, and nothing from this group, and many combinations of those. So I could give you constraints about the top K. I can also do this. Earlier, I give you a case where n is known. Okay, n is known. Okay, in this case, there is a time horizon. You know when to stop. For the secretary problem earlier, you know there's 100 secretary. So you can multiply 0.37 with 100 to get 37. However, there are cases where you have unknown n. That means you don't know where that n is. It could be 10, it could be 100, it could be 1,000. In this case, then, that earlier optimal strategy cannot work and will not work because we have infinite number of n. Right? You cannot predict whether it's 10, 100, 1,000, 10,000. So I cannot multiply 0.37 to that number. So my question to you is this, then what would be your optimal strategy? Okay? What would be your optimal strategy? Okay? So in some ways it's different because if you have $1,000 versus you have $2,000 versus you have infinite purse, it's different. Your strategy to explore this is very different, right? $1,000, you will be very, very careful about what you do. If I have infinite thing, I don't care. I just keep on doing round robin. So I get a long statistical accumulation. Then I don't know which one is best and so on and so forth. But if you have limited time, okay, what do you do? Okay, so this is a infinite. Oh, I'm sorry. I probably screwed it up a little bit. That was infinite time. So I don't know what time I need to stop. But this one is really the infinite arm. So you have infinite arms right here. Okay? And this arm could be what we call an advertisement or ads. So when you have infinite arms, then the question is, when do you actually stop? Or what, how do you actually, not when do you stop, how do you find out if you have so many arms right in there? Okay? How do you find out in this case when you have infinite number of possible arms? Well, this n is actually very large number of arms, right? So in some ways, for example, when Google wants to give you ads, each ad is like one of these arms. Why? When they give you an ad, if you click on the ad, basically, think about Google. Google pulled this arm by giving you the ads, right? And then you click on that ads. What does that mean? That means you like that ads. That means that you get a reward from that ads. That means you get a reward from this particular arm. And Google could be showing you many different ad displays, and you get nothing. No rewards, okay? So my question to you is this. What would be Google's strategy to send ads to you if they have a very large inventory of ads? Very large number, almost infinite number of ads that they can send to you, okay? Next, we can also have contextual bandit. Additional contextual information in online advertising that you could be given. Now let me say this, okay? In the typical MMB scenario, we only care about the reward, okay? Reward. So I only know the information when I pull, look at I get something back. That's it. But in contextual bandit, I could give you more information. More information, okay? For example, I could give you the past 20 times of this particular machine pull records, okay? And so on and so forth. So there is a context that I could add, or other features I could add into describing that. So it's not just like a reinforcement learning where I give you a reward and how much that reward, and that's it. I give you actually additional information, other features that you could use. And this is what we call a contextual bandit. Okay, this is also very interesting. Adversarial bandit, I asked Professor Song-Yong Lee earlier, GAN network, or adversarial network, right, is one of the things, right? This is different. This is not a two-player game. Although we have dueling Bandit, but it's not here. The adversarial Bandit means this, okay? You and I, we assume that this kind of multi-armed Bandit, the distribution and the machines do not change. Okay, the characteristic of the machine does not change. It's stationary. It's stationary. But what if this assumption is not true? What if the machine actually will change over time? For example, the physical machines, when they pull, you know, the mechanism will wear out, okay, and there's other things happen. So when you pull many, many times, it might deteriorate over time, right? So this assumption of same distribution may not hold. And this is what we call an adversarial, because you're trying to guess what that underlying distribution is. It's not stationary. So you need to figure out what is that moving non-stationary distribution for your particular arm, for the payoff. Okay? So time varying expected payoff for Band-Aids, expected as in online investment of financial markets and so on and so forth. Okay. So let me summarize this. I give you some variation, I give you the problem. I know it took me a long time to set up, but what is neat about it, you have to understand the problem in order to appreciate the solution. If you don't even understand the problem, you will not understand the solution. I'm sure that many of you are thinking about strategy right now. How do you actually do the optimal stopping? Okay? So basically what we want to say is this. Online learning is basically how to choose the best hypothesis for your data. Your data comes out, so when I pull this, I get a reward, or I don't get a reward. That's a data. My hypothesis is to say, this is the best machine, and this is the highest value that I'm going to get returned back. Right? So these are the things. I build up a hypothesis space, I do a prediction, and then I will change from that prediction, I will check the response, okay? And to see whether it fits the model that I have. If it doesn't fit with the model, that means I have to actually do, minimize the loss between the response and the prediction, okay? So I'm trying to build a hypothesis, I'm trying to build a hypothesis here of the data. That this is the hypothesis. This is the data. This is the prediction. This is the response. So we want to minimize this particular loop right here. So, I don't want to go through this. It basically says that we have a lot of data, okay, right now. And you saw this earlier, okay? And what I want to say is this, that for online learning is really good for volume and velocity. Velocity is the streaming data, so it's almost like it comes one after another, very similar to the secretary problem that we had, okay? So when do you stop optimally? When do you make a decision optimally? So for volume, we could also, it's good. Why? Because we could also reduce the amount of space that we need to keep. Okay, for all these algorithms, they are not batch mode. They could be done online. Okay, so that's why the volume and velocity, you can handle the big data for this 2V characteristic. Okay, so online learning for big data. Online learning is to solve problems involving sequential interactions between the data and environment. So in the big scheme of machine learning, online learning is just a small piece. You could do online classification, online advertising, online investment, and many other online stuff. Okay? So if you were to define how to solve this, let me just share with you what the basic difference is. If you've taken a machine learning course, this will be the equation that you will face all the time, right? Very simply put, I want to actually minimize a loss function between the input and what, I mean this is the label, and what my hypothesis right here. My hypothesis using the X label, the input label, multiplied by some kind of parameter weight that I have, and then this is actually the the real output. And what I want to do, I want to minimize the loss or the differences between these two functions, between the actual output and what my model of the output would be, right? So in this task, out of the 4 multi-armed bandit, I want to find out, for example, which one is actual the best arm, or how much I can actually get, okay? With some kind of regularization term. Okay, so what's the difference between online learning and this? Online learning is very kind of straightforward, okay? You can see that the difference between this equation and this equation is what? It's just the t, okay? And what that means is this, for every t, okay, every t right here, we need to find out that the loss function for a given t at any given time, okay, and the prediction at any given time. Because you know what, as time goes on, we make the best decision based on the best data that we have. And that's the best you can do, right? If you're so good, you know future data, then you're like God. But we don't. We can only do what we know the best. Now, different from the typical neural network training, typical neural training, they do a batch learning, they train that, and that's it. They stop. Then they go out there and try to do prediction tasks. Okay, and they go, oh, there's something wrong. Then what? They go back to the batch mode. They collect more data, and then they do this. Now, our thing is different. Our thing is that we continue to learn, continue to adjust as data comes in. Okay, that's the difference. So, because there is a T. So what we want to do is find out the W1, W2, W3, W4, WT at any given time. What is the best parameter that will describe our model, okay, to do that? Okay? And this is with the regularization term, to smooth things out. Now, to solve this thing, it turned out that you could, if you make the statistical assumption that these are IID, okay, independent, okay, and identical distributed, if you make that assumption, then you could solve this with what we call a recursive least square by substituting the F and the W into the previous equation. But most of you probably are more familiar with what we call a stochastic gradient descent. We do this all the time in many of the different learning algorithms. So typically, you just basically use this. This talk is not about doing this. I just give you the 2 ways that you could solve an online learning equation. Okay, so you could use this, or you could use this to solve your thing. Oh, I want to say this. For adversarial MAB, this is really a class of online convex optimization. So we might have to do something to solve this. Okay, so let me talk a little bit more about the characteristics. So for any online learning, we can actually look at in the 3 axes. One axis, whether you use full memory or use partial memory. If you use full memory, this goes back to almost like what? Like a batch mode. Okay, so this is almost like batch mode. So online learning is basically, you can think of it as a special instance of the batch mode that uses very little memory to store your data, okay, to process that. Okay. Feedback, whether you have full or partial, output feedback can be partial or full. In this case, the feedback could be full, meaning that they with context, with not only the reward, and how much is that reward. Or I could just give you partial, to say that when you pull, you win, but I don't tell you how much you win. In that case, I may not be able to calculate the maximum value, but I can calculate which machine seems to be the best machine. Okay, so it could be feedback, could be full or partial. The hypothesis could be, you know, independently, identically distributed, IID, or non-stationary. It could be moving. Okay, so the underlying MAB, each arm could be moving, or it could be something else. Okay? So, these are the 3 characteristics. So, if you were to do this, then we could actually have a taxonomy of based on this characteristic. If it's a full output, partial output bandit, convex, non-convex, stationary, non-stationary, these are the people in various years that we have solved these problems. In this talk, I'm going to talk about this one, and this one. 4 of these, because those are our work. Our work is in AAAI, in NIPS, in CIKM recent years. Okay, these are all very good conferences. So, and these are some of our work in full output convex situation. Okay. Okay. And for application, we can also talk about classification, regression, and ranking problems. And we're going to also talk about those 2 papers. Okay. So, from the application view, from the characteristic view, we could actually have different ways to look at the online learning problems. Okay. So I'm going to our recent work. So our recent work right here, we have Bandit algorithm research recommendation. So these, the red ones are the ones I'm going to introduce in this talk. Earlier, we talked about Frosh in the other talk that I'm not going to talk about here. But this is also unsupervised online hashing. So this particular work is not only online, okay, but it's also randomized. So it's online randomized algorithm. So this one was introduced in my previous talk. Okay, so we're going to just talk about these 2 things. Okay, so first, this work is actually was done in NIPS 2016. And this is actually very, very important work. If you want to actually read one paper from us, if you want to, this will be probably the best paper to read. Okay? And if you could read it, come join our group. We won't need you. Okay? This is really a lot of math. If you go to NIP's website, and this is a very good paper because it covers almost practically all different aspects about exploration. So let me explain to you what that means, okay? Pure exploration of MAB in the A/B testing. So A/B testing, you know what it is, right? So Microsoft, Google, whatever, they conduct A/B testing. So what they would do is, you know, they have one algorithm called A. They don't know whether your algorithm is good or not. They will do the A/B testing. They will randomly, or they're systematically, there are ways to actually test algorithm A and algorithm B without telling you which one they are using. That's the only way to actually find out whether your algorithm works or not. Okay? So this is pure exploration of MAB testing. They also do this in clinical trials because it's totally blind. Okay, in clinical trials, you cannot know whether you are eating the placebo or eating the real drug, right? The test drugs. Okay, so they do this wireless network crowdsourcing and so on and so forth. Now, because this is a real life problem, real practical world problem, there is a fixed budget. Okay, so this is not a theoretical problem. Theoretical problem, you might have infinite budget. That means that you have infinite resources to test out and try everything. But in here, we have a fixed budget to minimize the probability of error. So I give you $1,000, or I give you $500. How would you explore the best way to explore these 4 multi-armed bandits to give you the best result, right? A fixed confidence value to minimize the number of rounds. Okay, so if you could use minimum number of rounds, that will mean that you will actually do well or within the budget that has been given to you. So what I want to do is I want to get some kind of confidence level with minimum number of rounds possible. Okay? So, the situation is this. There are people here playing on 1, 2, 3, 4, right here. And these are the arms. Okay? And these are the round. Alright? So here, this person pull this, gets yes, pull this, says no, pull this, say yes, pull this, say yes, pull this, says no. So these are the rounds right here, these are the machine right here. So you have n arms, and a page view on the ith variance, reward, and click on ads. So again, this could be ads, and this could be the person who's looking at these ads and making clicks or not. Finding out the best arm is to basically finding out the variant with the highest average clicks. Okay, so you can see this as individuals, one person with different rounds, which doesn't make much sense, but another better way to interpret it is that this is actually many different people. So when I present this, okay, to many different people, which one would they click? Like for example, these two people, one click no, or one didn't click, one click on this particular ads, right? So these are the ads, okay? So what we want to do is find out that. Now, combinatorial, meaning that I want to try to find out all situations, okay, for pure exploration purpose. Okay? Basically, if you look at all the possible scenarios that we face, you really only face these more or less 4 different types of problems. And this is why I say this particular paper basically covers everything that we do. Okay? Let me explain to you what those 4 variations is. In most of the problem that you encounter, they will ask you either to find out the best out of the K, a best of the K sets. K could be 1, and that means I want to find out the best one. In this case, the red one, meaning I want to find out K is equal to 3, the top 3 best arms. Okay, so in this thing, they could be totally independent. That means each of the arms that you pull, they're totally independent. So I want to find out K, size K is equal to 1 or 3 or whatever, the top ones right here. Okay? Second thing is that I could also ask you to find out a path, explore a particular path, or a matching of a 1 to 1. Okay? Or a spanning tree that covers a set of nodes. Now you might say, wait a second, what does that mean? Now earlier it could be that this is totally independent. What this could represent, say, spanning tree, it could be that I want to find out, if I could find out there's some relationship between these machines, something like this, then I want to find out the best value under this spanning tree, or this matching terms. Now, look at this though. This is set, this is independent. This is basically one to many relationship, one to many relationship. This is basically 1 to 1 relationship. And this one will be many to many relationship. Okay? So I basically cover individual, independent. I basically cover 1 to 1 relationship. I basically cover 1 to many relationship. And I basically cover many to many relationship. So with these 4 basic things, I basically solve what we call the combinatorial pure exploration scenario. That means I basically solve, we believe, all cases. Okay, if you could actually do this. Okay? So, find the optimal set of arms satisfying a certain content by maximize the sum of expected reward. Right here. 4 cases. Okay? Really, in all your situation, tell me, do you have any more cases than these 4? Finding out the top, finding out 1 to 1 relationship, 1 to many relationship, and many to many relationship. You basically cover everything. Okay? So this is matching, is a 1 to 1 assignment. Okay? Finding spanning tree, the shortest path, is many to many relationship. Okay? And this one is finding the top K, which is they're all independent. Okay? So you basically could find all this. Okay. Basically, I'll just give you the intuition. The intuition is that each round you compute an optimal set of MT based on the empirical mean. Then you compute what we call a confidence radius for all arms. And compute an optimal set. This is an NT hat based on the new estimator. Then you estimate the arm with a lower bound and upper bound, and then terminate the algorithm when empty is close. Well, empty hat is close to empty. This is very typical learning algorithm. That's what it's doing. But let me explain to you what that means. What that means is this. You may begin your estimation right here. Where this is the uncertainty, okay? And this is the minus that. This is the uncertainty, okay? This could be the optimism for, according to historic and empirical mean. And this is actually the real mean. Okay, this is the empirical mean. This is the real mean. This is real. The empirical is the observed one. That might not be the real one that you want to be estimating. But as you getting more and more trials, guess what? Your confidence interval, or what? Uncertainty interval will continue to decrease. And then this will begin to move slowly to the optimal point. Okay? So look, there are two things happening. With only what you observed in the first time, your estimate may be here, with a very large uncertainty. Okay? But as you produce more and more experimental trials, as more you pull this thing down, this point will closely move to the optimal point. And that this uncertainty or the standard deviation will continue to decrease. So hopefully at the end, you will have something very close to here with a very small uncertainty and with very high confidence value. Does that make sense? So I could safely say that this is with high confidence that this is it. Okay? That's what we're trying to do. So basically, to cut it short, I don't want to go through the experiment and the thing. We basically come up with two general learning algorithms for a wide range of aim. We come up with an upper bound and also the lower bound. Okay? Compare with existing work. We're the first to come up with a lower bound for the top K problem, and we're the first upper and the lower bound for other combinatorial constraints. Okay? So this is a very good paper. If you could understand this paper, please come talk to me afterwards. Okay? Second work, this was I think CIKM paper. Okay? And this was called locally-sensitive linear Bandit model for online social recommendation. To put this short, earlier we say the arm and item, these are the corresponding to that, okay? To put this very, very quickly and short, what did we motivated is that we want to add social information signals into this set of arms. Okay? What that means is this, that because it is social, okay? So earlier we say that each arm is independent. That means that I pulled this arm and I pulled this arm, they're all independent, they are ID. But what if that's not the case? What if, for example, the probability of me looking at the ad and clicking on it is proportional to Jonathan, because we both are academics. So if they're similar ads, for example, selling a software package or a book on some technical topics that we both are interested, there is a high likelihood that we both will click on that ad because socially we're connected, right? With that signal, contextual signal, can we actually do better prediction? And the answer is yes. We can use the social information. Our goal is to integrate the social network knowledge into the Bandit algorithm, because the Bandit algorithm, it was not social, but we could do this. So what we do is, given the user an item with a feature vector at time, we can model this. Okay, so this is really the observed is equal to this plus eta right here. Okay, and what we want to say is don't worry about this. This is the algorithm part. Our final result basically says this, that we obtain an upper bound for the cumulative award if we assume that there is a social network behind this, and that social network is given to you, we're able to actually give you the upper bound for cumulative result. And what is interesting in this paper is, what we observed is this. You know, if you have a social network, your social network has a social network. So Jonathan is my friend, and Jonathan has his friend, and Jonathan's friend's friend has friends, right? So how many levels do we need to propagate? It turned out that we need to only propagate up to 2 levels. So I only care about me, Jonathan, and Jonathan's friend, and that's it. And that social network, if you even give me more social network, this will not actually increase. Okay, so giving me the whole complete graph, it will not make this any better. Just the first 2 levels of social network will help to make this good. Okay? So, next result, I'm going to go a little bit quicker, is constructing a reliable gradient exploration. Basically, this is done in the ranking. Okay? When you rank something on online learning to rank something, for example, in social, Google gives you, when you search for Java, for example, Google will give you all the terms in ranking, right? But Google never tell you that the first one is, has a score. And Google will not tell you the second one score, or third one score. There's no numerical score. They're only a ranking in search, right? And for us is this, how can we actually help using online learning to search, to help the search engine to work automatically, okay? And that's very, very important. So, 3 challenges. How do you generate exploratory future parameters? How to demonstrate the result for comparison, and how to update a parameter based on user feedback. Why is that? I'll give you a very simple example. When you search for the conference, say NIPS, if you search it right now, what do you think Google will return? Is it the 2016 NIPS, 2017 NIPS, or 2018 NIPS? What do you think? If I search for a good conference right now, NIPS was held in November last year. If I search for NIPS right now, what do you think the context should be? Most likely, I care for either 2017, which just happened, or 2018, right? By the clicking of these people, clicking the people's feedback, whatever they click, whether it's 2017 or 2018, my algorithm, online algorithm, might adapt to that. So maybe right now, I'm still clicking on 2017 NIPS result. But in another 3 or 4 months, that will be automatically changed. Why? Because people will not click on 2017, they will click on 2018 NIPS to see when is the deadline, what are the workshop, and so on and so forth. These are what we call the online signals that are coming in, okay, that we can actually change. So this is what we call online learning to rank, because the ranking order is an implicit feedback from your thing. So update or not, so A, B, if you have some ranking A, B, C, D, E, but the user is clicking A and B, okay, and so on and so forth. Should you actually have a new exploratory parameter for them to actually click and find out what is there, okay? So Google might actually explore your preference and your clicks by sending you a different order and see what you're clicking to understand your preference, okay? And this is what online learning exploratory is all about. Anyway, to cut this story short, we use what we call the dueling Bandit gradient descent to calculate this problem, okay? So by getting information from PageRank and from other exploratory weighted space, we're able to actually rearrange the ranking, okay? And to demonstrate that our online ranking actually is better, okay? So here's the algorithm, okay? Let's continue the algorithm. Here are some data sets. I don't want to talk about it. Our methods. Okay? To summarize is this, we come up with two algorithms, dual point DBGC and a multi-point deterministic gradient descent. And we compare with one directional exploration or multiple way of exploration, and our two algorithms outperform the existing method. It was done in CIKM. Okay? I'm going to just say a little bit about online learning for imbalanced data. Okay? Online learning for imbalanced data goes like this. In our real world, we have lots of data. And typically, the data could be balanced. That means the number of positive examples and the number of negative examples are equally, more or less equal. But in many situations, like for example, medical cases, where the positive, like disease cases, are only very few. But the typical population is normal. Okay, so it's negative cases is hundreds or 1,000 times more than the disease cases, because they only have few disease cases. Okay? In this case, what we're doing is this. What we call this is called imbalanced data. Imbalanced data. Okay? Now, if you imagine that this is a problem, the number of samples for some classes is much larger than us. The issue is, first of all, how do you actually, if you look at this, there are some dots here and there are lots of dots here. How do you actually separate these dots, solid dots, from the light blue dots? It's very hard. Good performance, how do you actually get a good performance model? So our consideration is this. Kernel techniques for imbalanced data, and this is the key point. What if you have a fixed budget? Okay? If you have an infinite number of budget, this is very simple. You just continue to try until you're done. But if you have a fixed budget, you're doing it online way, as disease cases are actually coming in, what do you need to do actually to test out your model? Can you do this on a real-time online basis? Okay? And this is what we did for this particular one. Okay? So, I don't want to say it, but this is an imbalance ratio, 1 to 140 thing, and then shuttle one is 1 to 328. So the positive and the negative is this much off. Okay? So what we want to do, the goal is to seek a nonlinear decision function for imbalanced data with a fixed budget. So this is actually the boundary that we want to seek. But what we want to do we want to seek this boundary within a fixed budget of exploratory things. For example, these could be patients that we might need to pay to get a sample from. So each of the tested sample will require some budget. Okay? So here, what we say is that what is the minimum number of patients that you could test in order to get this imbalanced sample function? And this is a work in that. Our result is basically, don't worry about these techniques, but we achieved, again, best performance of all the imbalanced data sets. And this is, again, insensitive to parameter. We proved the regret bounds as an order of square root of t, and the t is the number of samples. Okay, so this is a work for online imbalance thing. So I'm going to skip this. Don't worry about this. Okay. So to summarize this, what we have here is this. The NIPS paper 2014, 15, 16, 17. These are the papers. We did this partial information bandit, full information bandit in these two. The application is earlier we did the ranking, their classification and do recommendation and so on and so forth. These are the achievement of our papers. Some got the best theoretical guarantee. Some beat the other methods. This paper, in fact, was runner-up to the best paper. So we were very close to be the best paper for CIK in 2016. Okay, and then this one would be other methods as well. Okay, so how do we go forward? Go forward is this. Adversarial environment, we did not study that because it was too broad. Adversarial is meaning non-stationary characteristic. Okay? So you could have approximation, variant distribution. We could actually do approximate maximization. Most of our assumption is convex. Okay? Most of our assumption, the optimization that we want to do is all convex. But what if they're non-convex? How to do that? Social related bandit, we could actually explore other complex structures, and we could model other complex behavior among users. Okay, so these are some of the things we could do. Thank you. I thank my PhD students. So in conclusion is this. Today, I show you online learning is an effective approach to handle incoming data based on sequential decision problem, secretary problem, marriage problem, and so on and so forth. I also show you some characteristics and applications of the taxonomy of online learning. And lastly, we presented 4 of our recent work on various recommendation, ranking, on classification, and so on and so forth, with different characteristics. So this really summarizes our study in the past few years. Okay? So I leave you with this. I hope you guys know this movie is from? What is this from? What is this? Forrest Gump, right? Forrest Gump. You know Forrest Gump, right? And the famous, probably one of the more famous sayings says this. My mama always said, life was like a box of chocolates. You never know what you're gonna get. Okay? So online learning is exactly like that. You don't know what is going to come out, because when you pull that thing, you can only know there's a reward and there's no reward. But how do you make that best judgment whether that is the best machine? You don't know. When you are dating somebody, you ask, is this the right person? Should I marry this person, or should I date another person? You don't know. But what's interesting about this is this. In fact, this is a famous saying, but there is another saying that Forrest Gump, Mrs. Gump said, I think is what is more important. And Mrs. Gump said this, you have to do the best with what God gave you. Okay? You have to do the best with what God gave you. And this is what online learning is all about. You have to make the best decision with what the information gives you. But you got to have a strategy, right? To know when to explore and when to exploit. And with that, I finish my talk. Thank you very much.
I think we have time for a couple of quick questions. Anyone?
Any questions?
Yes. Microphone, please.
Could you explain a little bit more about how to deal with the imbalanced data? I'm a little bit confused about that part.
Okay. For that imbalanced data, the idea basically is this. We actually have been working with imbalanced data a long time ago. Okay? But the key point here is this, that you have a fixed budget. A fixed budget. That means that you cannot explore as long as you want. You only can explore maybe 10 times. And we came out with a strategy using online learning to explore with a fixed strategy. Okay? In some ways, in that particular case, is very similar to what we call active learning. I don't know whether you know active learning. Active learning basically is given, you are given the resource, okay? And you can ask questions, maybe ask only 10 questions. So which one are the best questions that you ask, okay? So let me give you some intuition about that, okay? Very quickly, sorry. Very quickly, let me just go back. Oops. Okay, so let me ask you this. If this is the boundary that you're exploring, right? If you could only ask 10 questions, now, which are the 10 questions you're going to ask? Like, for example, if this is the boundary that you want, right? where are the questions, or where are the points that you want to look at, whether it belongs to one class or the other class. Some points here, or points along the boundaries. Which one are your best? Will tell you the most information. If this is the boundary, right? Would these points tell you more information than say the boundary points? Which one will give you more information? Which one? Boundary points, right? Right? Because these points, it doesn't matter. If you test 10 samples here, you basically get the same class. It tells you nothing. If you have 10 questions, what you want to be able to do is basically get 5 in one class and 5 in the other class. So you have a balanced thing, right? But this is imbalanced. So which one would you pick? How do you pick from a large class? You don't want to just pick randomly. You really want to pick those things along the border that what you expect. That's the intuition. Okay? So imbalanced thing, what you don't want to pick, again, something that is common. You want to pick those cases that you're not sure whether it's in one side or the other side. Right? And you want to pick, in fact, 5 positive and 5 negatives so that you balance the data out. And that's what this is all about. It gives you a strategy to pick. Fixed budget, you could only pick 10 or pick 100. How do you pick that? And we give you a strategy on how to do that. That's what imbalance is. Okay? Any other things?
That's actually very similar to this question.
Okay.
Or I have simple question.
Yes.
So the slide that you show very basics, different about the machine learning, I mean the offline learning and online learning.
Yes.
And I'm not familiar with this kind of words, but I just wonder that how they usually do with the online learning to adjust the cost function. I mean, so do they have to retain the whole data? I mean, the old data and the new data together again, or they just update the new data to the new hypothesis, new loss function? So what is the way to do that?
Yeah. So in a pure offline or batch mode, right? The data is collected. And no new data is coming in. So I collect this data, I process this data, the way that you do machine learning right now. You collect the data, okay, and then you run your model, and then that's it, right? If you get something wrong, you go back to your data set and you look at it, you change your parameter, and the data set really doesn't change. Our thing is that, what if that data continue to increase and change over time?
And you reconsider the old data again?
You don't need to. That's 2 different methods, right? One is full memory, and one is partial memory. The partial could be 1. It could be a window. It could be everything. Right? If I only store 1, okay, then you have to do with 1. If I store a window like 30 days, like for stock prediction, I might just store 30 days. I don't need more than that, right? Or I can store the whole history of the stock data. You can do that too. There's no difference. But for batch mode, okay, it's different because we have to make decisions right there and then about what to do for online learning. That's the difference.
Okay.
Okay?
Thank you.
Yep.
Okay, we are running out of time. So actually, please do come up before I take a break. We're going to take a group photo, and then go for a short break, and then come back at 3 o'clock. Please come up to the front. We'll take a group photo. Everybody come up, please.
Okay.
You want to organize this?
Yeah, that's the scan, and then we use face recognition system to figure out what kind of thing we see.
Yeah, you can do that.
Well,
I'm just a messenger. Let's go.
ไปแล้วได้
You two this one. Can you see everybody? Is that too far? Really? We have it? Thank you, Julian.
So you sleeping?
I don't know. Am I? It's only 3. I will listen to you come to the
My flight is 9:45.
lounge access? Let's go together. Yeah, sure. Let's go together. Okay, so now you have 2 lines. Other part is social. Good. Around 4. Can you actually go exit? And then we just go. The other part will shoot it again.
So you fly at 7, right?
Yeah. So 4
Or
to
be there at
5
5.
to get there, so 12. Right? You need it.
Very soon.
Come to Hong Kong.
Okay.